Welcome to Theory of Computation. This is lecture number 43. We are continuing our study of space complexity, and we have defined two very interesting classes. One is what we call L. L stands for log space, and the other is NL. NL stands for non-deterministic log space. NL is an extremely interesting class, and the L versus NL question is of the same category as the P versus NP question, except that the P versus NP question is about time and it compares determinism versus non-determinism, whereas the L versus NL question is about space complexity. We already saw one question about space complexity, which was the P space versus NP space question. That question was resolved by Savage's theorem. However, the technique used in Savage's theorem is not powerful enough to separate N, L, and L. On the other hand, it's not powerful enough to show that these two classes are equal either. So, when we study the L versus NL question, we are forced to think of new ideas. Well, we realized that the unresolved P versus NP question will be resolved in the negative if we were able to show that NP is not equal to co-NP. However, that's not the case with L and NL. What we can do is we can show that NL is closed under complementation. That is, NL is equal to co-NL. What this means is that this way of attacking the NL versus L question is not possible. NL turns out to be a space complexity class, a non-deterministic space complexity class, which is closed under complementation. That's a very unusual fact. If you think about non-determinism, being closed under complementation is not that obvious at all. But when you think about deterministic complexity classes, it's obvious that they must be closed under complementation. Well, for example, if you have a polynomial time Turing machine that accepts some language and it's a deterministic Turing machine, then all you have to do is change its accept states or accepting configuration and make them rejecting, and the reject states into accepting, and the new machine will actually accept the complement of the original language. Furthermore, it will use the same amount of resources in the sense that it will use the same amount of space that it was using before, and it will use the same amount of time that it was using before. Therefore, the deterministic complexity classes are trivially closed under complementation. However, that's not the case with non-deterministic complexity classes. For example, if you take a non-deterministic Turing machine and let's say it uses some resources, some amount of space and some amount of time, and accepts a language, if you simply complement the states, accept and reject states, that is, you make all the accept states into reject states and all the reject states into accept states, the new machine is a non-deterministic Turing machine. It does use the same resources, but it does not accept the complement of the language. That's because the criteria for acceptance in a non-deterministic Turing machine is that at least one branch should accept, and the criteria of rejection is that all branches must reject. And when you simply complement the states, you do not get a Turing machine that accepts the complement of the language of the original machine. Therefore, to show that non-deterministic complexity classes are closed under complementation is a tall ask, and it's not trivial at all. Well, we have done that already. In fact, what we did was we proved that non-deterministic polynomial space is closed under complementation. However, we took a very roundabout route. What we did was we showed that NP space was equal to P space by Savage's theorem. So, once we know that NP space is equal to a deterministic complexity class, P space, therefore, it must be closed under complementation. Well, the L versus NL question is not that simple. We have not been able to capture NL with any natural deterministic complexity class. So that plan is not going to work. The purpose of today's lecture is to actually prove that NL is equal to co-NL, that the language non-deterministic log space, the set of all languages in that can be recognized in non-deterministic log space, is closed under complementation. So that's going to be today's lecture. We will start looking at a proof, an outline of a proof that will show that NL is equal to co-NL. Well, what we have been doing in complexity theory so far and computability is previously we have been separating classes. We, for example, proved earlier in this course that recursive languages and recursively enumerable languages are two different classes of languages. On the other hand, we have also spent a lot of time on theory of completeness, NP completeness, P-space completeness, and so on and so forth. We have hardly looked at proofs which show that two complexity classes are equal. We did look at one proof, which was Savage's theorem, which told us that P-space is equal to NP space. Here we will see another example of a non-trivial result which shows that two complexity classes are equal. And the way we go about doing that is very simple. What we do is the complexity class that we want to study, well, we define a complete problem in there. Once we have defined a complete problem, then our task becomes simpler. We will show that a problem called path is NL complete with respect to log space reducibility. And it's important that the problem be complete with respect to log space reducibility. Once we show that, then we will show that the complement of path is also in NL. So, since path is NL complete, its complement is co-NL complete, and a co-NL complete problem is in NL, therefore the two complexity classes must be equal. However, to show that the complement of path is in NL will require us to come up with a non-deterministic algorithm. And this algorithm is not going to be trivial at all. In fact, far from it. It's extremely ingenious. And we'll see how it is crafted out by putting small ideas together, and we'll come up with this algorithm which will eventually give us our result. So let's begin today's lecture. What we will show is that there is a problem path that is NL complete with respect to log space reducibility. The second thing we will show is that the complement of path is in NL. This means that path is in co-NL. Now, one thing to notice about log space reducibility is that a language is reducible to another language if and only if the complements also satisfy the same relation. Formally, what we note is that if A is log space reducible to B, then A complement must be log space reducible to B complement. And the proof of this little fact is that if A is log space reducible to B, then there's a log space transducer that reduces A to B. Well, the same log space transducer will reduce A complement to B complement. So this is not a very complicated theorem to prove, it's just an observation. This theorem implies that path complement is co-NL complete. Since we will also show that path complement is in NL, this would tell us that NL is equal to co-NL. Why would this tell us that NL is equal to co-NL? Well, let's pause for a moment and think about it. Take a language which is in co-NL. Well, since this language is in co-NL and path complement is co-NL complete, therefore there is a log space transducer that reduces this language to path complement. Now, since we show that path complement is in NL, we can use the log space transducer combined with the algorithm that I give you for recognizing path complement using by a non-deterministic log space Turing machine to come up with an algorithm that accepts A using a non-deterministic log space Turing machine. So in some sense, we're just using transitivity of log space reducibility in order to show that NL is equal to co-NL. Now let's define this problem path. It's going to be a very natural problem. I will define this problem and then we'll see why this problem is NL complete and why therefore its complement is co-NL complete. So let's say that we have a graph G and it's a directed graph and we have two distinguished vertices in it. One is S and one is T. S stands for source and T stands for target. What we do is we define the path problem or the path language to be the set of all triples G, S, T such that there is a path from S to T in the graph G. Thus the computational question is, we're given two vertices in the graph and we have to decide if there is a path from the first vertex to the second one. This problem is also sometimes called ST connectivity. So it's a very, very simple problem. You are given a graph and two designated vertices and you are asked if there is a path from S to T. To gain a bit more understanding of this problem, let me just comment that suppose I give you this question as a computational question in an algorithms class and I ask you to design an algorithm for this problem. So what you will have to do is design an algorithm which takes a directed graph as an input and two designated vertices and tells us if there's a path from the vertex S, the source, to the target vertex. Well, how will you go about it? You have studied many algorithms, for example, depth first search or breadth first search. They both will work well for solving this problem. All you have to do is start depth first search from S and see if any of the path reaches T or not. If you use breadth first search, you will actually be able to find the shortest path from S to T if one exists. So this is not a very difficult problem to think about. You have looked at this computational question. Now it turns out that this computational question is NL complete. Before we think a bit more about this problem, let me comment on these search problems that we have been thinking about. Searching problems in graphs are extremely general problems and they tell us a lot about Turing machines and therefore a lot about complexity classes. Intuitively, what you can do is think of a Turing machine which is given an input X. And now you can think of all possible configurations of this Turing machine as vertices. And you place an edge between two configurations if you can go from one vertex to another vertex using one step of this Turing machine. If one configuration yields another configuration, you place an edge. Now, if you want to know if this Turing machine accepts a given input, all you have to do is ask yourself if from the initial configuration, which is a designated vertex in this graph, to the final configuration or to a final configuration, if there is a path or not. So by asking an ST connectivity question on this graph, you find out whether M accepts an input X or not. This idea is extremely useful. So for example, when we used Cook-Levin theorem, what we were doing is it was a non-deterministic Turing machine and therefore this graph was not going to be a linear graph. And what the Cook-Levin theorem was doing in some sense was saying that if you can provide me with the proof, with the whole path, then I will accept. And that's why SAT was able to express this idea in Boolean logic. That's why SAT turned out to be NP-complete. Similarly, if you remember when we proved that TQBF was P-space complete, it was also asking whether a polynomial space Turing machine, a non-deterministic polynomial space Turing machine can go from the initial configuration to the final configuration. So it was also asking about a ST connectivity type question in a very large graph. And that idea will show us also that path is NL complete. Let's continue with our discussion on path. Now, if you remember the proof of Savage's theorem, then Savage's theorem told us that path is in deterministic space log squared of n. But what we want to do is not to say that path is in deterministic log squared space, or it can be solved by a deterministic Turing machine which takes space log squared of n. We want to show that it can be solved by a non-deterministic Turing machine in space order log of n. So what we want to do is show that path is in NL. So that would be the first part that we want to show. And after that, we want to show that path is NL complete, or every language in NL is log space reducible to path. So these are the two tasks that we want to start with. So let's begin. To see that path is in NL, we recall that non-determinism allows us to guess. Thus, given S and T, we can try to guess the path from S to T and accept if we find one. However, we are only allowed to use a small amount of space, and therefore we have to be a bit more careful. Remember, in non-deterministic Turing machine, we had the power of guessing. So you're given a source vertex and you're given a target vertex S and T, and you want to design a Turing machine, a non-deterministic Turing machine, whose at least one branch will accept if there is a path from S to T. Otherwise, all branches should reject. So one idea would be to guess a path from S to T, and then so each branch will take a different path or a different potential path. Once we have taken a sequence of vertices which is a potential path, then we can check if that is actually a valid path from S to T in our graph. It is. If it is, we will accept, otherwise we will reject. Now, the branch that guesses the right path is surely going to accept if there is a path from S to T. On the other hand, if in the graph there is no path from S to T, then all the guesses are going to come up with sequences which are not valid paths in the graphs from S to T, so all branches will reject. So this seems like a nice idea to write down a simple non-deterministic algorithm. The problem with this algorithm is, once you write down the path that you're guessing, that takes too much space, and we cannot afford that much space. Remember, we have only log n space, order log n space, where n is the number of vertices in the graph. So we cannot afford to remember a whole path. So let's look at this new idea which saves space and does the same thing. So let's consider the following non-deterministic algorithm. The input to this algorithm is going to be a graph and two vertices, two special source and target vertices in the graph. So the input to this problem is what we expect. It's a graph with two special vertices. One is the source and one is the target. What this algorithm does is it sets the current vertex to be the source vertex, and then it runs the following loop n times. In this loop, every time it guesses a vertex W, and then what it does is it checks if V comma W is an edge in the graph. If it is not an edge in the graph, then it rejects. Otherwise, it checks if W is equal to T, then it has found a path from S to T, so it accepts. Otherwise, it updates the vertex V to be W. So here is your very large graph, and there's the starting vertex S. You start from there. And here is T. Now, every branch of this algorithm is trying to guess the new vertex. When it guesses the new vertex, it forgets about the previous path that it has already traversed. So it guesses a new vertex, and if there's an edge going from the current vertex to the new vertex, it just moves there. So since the algorithm starts from the source vertex, at any point in the algorithm, either the algorithm has rejected or it has traversed a path from S to the current vertex. If the current vertex turns out to be T, then the algorithm has actually discovered a path from S to T. On the other hand, if the current vertex does not turn out to be T, then the algorithm tries to take one more step. Now we know that if there is a path from S to T in a graph of size n, then there is one which has length at most n. Therefore, the algorithm only needs to try this n times. The clever thing here is that the algorithm is only remembering one vertex, the current vertex on the path, at a given time. What it does is when it makes the next guess and it realizes there's an edge from the current vertex to the next guess that it's made, it just updates the current vertex and forgets about the previous vertex that was the current vertex, thereby saving space. So how much space would this algorithm take? Well, let's look at this algorithm again and see. So this algorithm has a loop that's running from 1 to n, which is just a counter. And the other thing is it has to only remember the current vertex v. The maximum value of the counter is n, and also there are n vertices in the graph. Thus the total used space by this algorithm is order log n. Since the graph has n vertices, we can without loss of generality assume that actually the vertices in this graph are labeled 1 through n. Therefore, v can also be stored in a counter which is log of n bits long, and of course I will be stored in a counter which is log of n bits long. Thus, this algorithm only uses two counters. What does this algorithm achieve? Well, it solves the path problem non-deterministically. If there is a path from S to T, there is at least one branch, one sequence of guesses which will make this algorithm accept. On the other hand, if there is no path from S to T, then all guesses, all branches will reject. So this shows that path is in NL. So this algorithm is trying to guess a path. The trick is that it does so by guessing one vertex at a time. It does not bother to remember the previous vertices of the path, thereby saving space. So the trick is to save space. When you're designing non-deterministic space-bounded algorithms or space-bounded algorithms, then you want to save space at the cost of time. Of course, in this case, time is really not an issue. Here what we're doing is we're saving space at the cost of allowing lots of non-determinism. Think about when you use this algorithm on a real graph, what would happen? Most of the branches, if there's a unique path from S to T and there are many other paths in the graph, the algorithm, most of its branches are just going to guessing wildly and they will reject. Only one branch will accept, which will correspond to the unique path from S to T. However, that's not an issue in this case because we are only trying to show that path is in NL. Now we would like to show that path is NL complete. So let's take a language A in NL. Then there is a non-deterministic Turing machine M that accepts A. Furthermore, we know that this non-deterministic Turing machine takes only log space. What we would like to show is that this language A is log space reducible to path. How are we going to do that? Let's look at that. Let's consider an input X to the non-deterministic Turing machine M. The non-deterministic Turing machine M will perform a computation. Let's think of making a graph as follows. The vertices in this graph are going to be all the configuration of this Turing machine M on the input X. Let me elaborate. Well, remember that we said that when we are going to talk about space-bounded Turing machines, then what we will do is we will actually have an input tape that the machine will be allowed to read over and over again. There'll be a work tape and there'll be an output tape. So the configuration of a non-deterministic Turing machine or a deterministic Turing machine, which is space-bounded, is on an input X, can be given by only two things. Firstly, you tell me what's on the work tape, so you have to tell me all the contents of the work tape. And the second is, you have to tell me where the head is on the work tape. And thirdly, you have to tell me where the head position is on the input tape. Notice that the input does not change. So the work tape, the contents of the work tape and the positions of the two heads completely determine what the configuration of a space-bounded Turing machine is. For you to be able to know what exactly the configuration is, you have to know the input. But suppose the input is fixed for some application, X is fixed, then this information is enough. The contents of the work tape and where currently the head positions are. You don't really need to know what is on the input tape because that's never going to change. So a configuration can be written down without writing the input over and over again, and that's very important. So we think of this graph, and the vertices of this graph are configurations of M on the input X. The second thing is that we connect a configuration C to C prime if and only if C is going to yield C prime in one step. So we think of this large, huge graph which consists of all configurations of the Turing machine M on the input X. And so X will not be written once we write these configurations. It's fixed for all configurations. And the second thing is we will connect a configuration to another configuration if the machine can go from the first configuration to the second one in one step. And this way we define a graph. Well, this graph is going to be summarizing how M will behave on the input X. To find out if M accepts X, all we have to do is find out if from the vertex that corresponds to the initial configuration, if we can reach a vertex that corresponds to the final configuration. So this graph summarizes the computation of M on X. And if we can compute this graph using log space, then we would have reduced our language A to path. Because all we have to do is to solve a ST connectivity problem on this specialized graph, and if we can compute this graph, then we would be done. Now what we note is that a configuration C of the non-deterministic Turing machine is specified by three things. Number one is the contents of the work tape. So firstly, I have to tell you what is written on the work tape of this non-deterministic Turing machine. And that's a piece of information you need to know for knowing what the configuration of this Turing machine is. The second is the position of the head reading the work tape. The third thing is the position of the head reading the input tape. Thus, all configurations are given by triples C equals W, I, J, where W is the contents of the work tape, and the machine is currently reading the ith symbol on the work tape and the jth symbol on the input. Well, W is not going to be very long. In fact, since the machine runs in log space, therefore the length of W is going to be logarithmic in the length of the input that was given to the Turing machine. I, which is actually the pointer or the index of where the work tape is being read, is also going to be a very small number, logarithmic in the size of X, the input that was given. J, where the input is being read, can be a number between 1 and the length of the input, X. However, we can write down this number in binary, and that is going to use only logarithmic space. Thus, all configurations require logarithmic space to describe. And since the machine is taking only logarithmic amount of space, therefore we can compute all possible configurations and output them. Furthermore, if one configuration is given and another configuration is given, we can easily find out if the first configuration yields the second one or not. Or in other words, if you give me one configuration, I can easily output all the configurations that follow from it in one step. Thus, in summary, what we see is that since M runs in log space, thus all such configurations can be enumerated in log space. It is also easy to see that given any configuration C, we can compute in log space the configurations that are reachable from C in one step. Thus, we can output the edges of this whole graph. So, what we can do is output the vertices of this whole graph, this computation graph of M on X, and all the edges of this whole graph, and this only requires us to use log space. Formally, let us denote by G sub M comma X the graph described above. And let's consider the following algorithm. This algorithm takes as input X. It computes G sub M of X in log space and outputs it. So it outputs G M of X comma Ci Cf. Here Ci is the initial configuration of M on X and Cf is the final configuration. This is a reducibility that shows that A is log space reducible to path. So what we did was we took an arbitrary language A in NL. We said that there must be a non-deterministic Turing machine which recognizes A, and we said that based on this non-deterministic Turing machine, we could come up with a reducibility given by the algorithm that was shown to you, which reduces A to path. And since we have been able to reduce an arbitrary language in NL to path, therefore path is NL complete with respect to, of course, log space reducibility. Next, our task will be to show that the complement of path is in the class NL. This is not going to be a simple theorem. We have to first understand this problem very carefully. So now what we want to do is we want to show that NL is equal to co-NL. And as we have discussed before, it suffices to show that path complement is in the class NL, because that shows that path is in co-NL. And by our previous arguments, that shows that NL must be equal to co-NL. Well, this is the beauty of having complete problems in complexity classes. When you have a complete problem in complexity classes, instead of paying attention to the whole complexity class, what you can do is pay attention to one concrete problem. And if you can show something meaningful about this one concrete problem, then in some sense you can talk about the whole complexity class. What we did was we established the completeness of path for NL, and now instead of working with the whole class NL, we can work with this one tiny little problem, this problem path or ST connectivity. And if we say something intelligent about it, it applies to the whole complexity class NL. In this case, what we will do is we'll show that the complement of path is also in NL, and this would prove that NL is equal to co-NL. But what does it mean for the complement of path to be NL? Let's first understand that very, very clearly and then go about this task, which is not going to be very simple, but we'll break it up into pieces and understand the algorithm piece by piece. This is a highly non-trivial algorithm that we will be looking at. Our goal is to design a non-deterministic Turing machine that takes as input a graph and two vertices S and T. The Turing machine M must have the following properties. So this Turing machine must accept path complement. What does it mean for a non-deterministic Turing machine to accept path complement? Let's just spell it out. The first thing is that if S is connected to T, then all the branches of M must reject. If S happens to be connected to T, then this triple GST is going to be in the language path. Therefore, this triple is not going to be in the complement of the path, and therefore we must reject it. And for a non-deterministic Turing machine to reject, all its branches must reject. So, if S is connected to T, then all branches of M must reject. The second property it must have is that if S is not connected to T, then at least one branch of M must accept. Once again, here we are using the acceptance definition for non-deterministic Turing machine. We say that a non-deterministic Turing machine accepts the input if at least one branch accepts. Now, if S is not connected to T, then G, S, T is not in path, and therefore it is in path complement. Since it is in path complement, we want our non-deterministic Turing machine to accept that input. And how does a non-deterministic Turing machine accept? At least one branch of it must accept. The other branches could be doing acceptance or rejections, it doesn't matter, but we want at least one branch which must accept the input. And that's going to be the saving grace in this theorem, as you would see. The third property that we must take care of is that M must run in non-deterministic log space. So M must be a non-deterministic log space Turing machine. So the restrictions we have are we can only use log space. That is the restriction we have. We cannot use a lot of space. And the other restriction we have is that if S is connected to T, then all branches must reject. There's the third requirement, which is that if S is not connected to T, then at least one branch of this Turing machine or this non-deterministic algorithm must accept. So let's go about designing such an algorithm. Well, let's first think about what is the major difficulty. The problem is that non-deterministic Turing machines are very good at finding things. However, this time we are asked that non-deterministic Turing machine should accept when there is no path from S to T. So it is a very counterintuitive problem from the point of view of non-determinism. See, non-deterministic Turing machines are good at finding things. So for example, if we want to say that we want to accept all graphs that have a Hamiltonian cycle in them, then a non-deterministic Turing machine simply guesses the Hamiltonian cycle, and if it finds one, it accepts. They're not very good at finding or not finding things or making sure that things do not exist. In this case, we're actually telling exactly what is the opposite of what the power of non-determinism is, that is to guess. Now, if we were to say that if there's a path from S to T, then accept, then a non-deterministic algorithm almost stares us in the face. We try to guess a path from S to T. But now we are saying that except if there is no path from S to T. And what you cannot do is guess a non-path. Because if you guess a non-path, that just has simply no meaning. How do you guess the fact that there is no path from S to T? And this algorithm will in some sense do this very, very cleverly. So let's see how we will do this. This is going to be a difficult problem to solve. So we start by solving a much, much simpler problem. Let's say now that we are given the following information. So we will solve the problem in question later on, but before that what we will do is we'll solve a simpler question, and this simpler question that we'll solve is going to show us techniques which we'll use later. Not only that, this simpler problem is going to be also a part of our eventual solution. So let's look at this simpler problem. Suppose we are given an input graph with two special vertices S and T, and we are told a magic number C. C is the number of vertices in G that are reachable from the source. Now what we have to do is we have to design a log space non-deterministic Turing machine, and this Turing machine will reject all inputs where S is connected to T, and at least one branch of this Turing machine M will accept if there is no path from S to T. So what we're doing is solving a simpler problem. This problem is simpler because somebody is giving us extra information. The original problem gave us a graph and a source and a target. Now we are also given a number C. And some kind-hearted person has gone through this graph and found out how many vertices are reachable from the source. And they give this information to us for free. So we are told that this graph has, say, 50 vertices that are reachable from the source. And our goal is now to accept if there is no path from S to T and reject otherwise. So this is not really much simpler, but it turns out that this information C is very, very useful, and we can use that to design a non-deterministic Turing machine that we want. Let's see how this is done. So this problem is easier to solve. Let's look at an overview of a non-deterministic algorithm that solves this problem, and then we will try to improve it. The input to this non-deterministic Turing machine is G, S, and T, and a number C. Furthermore, it is promised that there are exactly C vertices that are reachable from S. So, the input to this is the graph, the two vertices, source and target, and a number, plus a guarantee that exactly C vertices are reachable from the source. And our task is again what we set out to do. Now let's see how we will go about doing this. What we will do is we will guess the C vertices that are reachable from S. And now for each one of those vertices we will try to verify if our guess was correct. So if somebody tells us there are exactly C vertices reachable from S, let's just go ahead and guess them. And then verify that these vertices are reachable from C. And if all these vertices are verified to be reachable from C and T doesn't pop up there, then we have somehow figured out all the vertices which were reachable from S, and none of them happen to be T. So T is not going to be reachable from S, and therefore we can safely accept. That's the idea. So we guess C vertices, and for each one of those vertices we will guess a path from S to VI. We'll verify this path from S to VI by checking the edges of G. And if the path is not valid, then one of our guess was wrong. Either we guessed VI wrong or we guessed the path wrong, so we'll reject. However, if all these paths we are able to find and we are able to verify that all these VIs are reachable from S and none of them turns out to be T, then we will accept. So this is the overview of the algorithm. Right now, this is not a log space algorithm. Not only it's not a log space algorithm, the algorithm is very vague. Now let's refine it and see how we'll get a log space algorithm. This machine does solve the problem. Let's first see why. For it to reach the accept state, it would have to verify that at least C vertices are reachable from S and T is not one of them. Furthermore, if T is not reachable from S, then the machine that makes all the right guesses will accept. Thus, at least one branch of this Turing machine will accept, if and only if T is not reachable from S. But how much space does this algorithm take? So, if we were to implement this non-deterministic algorithm, how much space would it take? There are two problems in this algorithm. It has to guess and remember the set V1 up to Vc. The second problem is it has to guess a path from S to Vi and remember and verify it. So it has to guess the set of vertices reachable from S, and it has to, for each vertex, then guess a path. Now this is too wasteful. This is too space wasteful. So we use the previous trick that we used to solve the path problem. Remember in the previous problem where we showed that path was in NL, we did not actually guess the entire path. We guessed it one vertex at a time. So here we have to guess a set and then a path. So what we'll do is we'll guess one vertex at a time, and we'll also guess the path one vertex at a time, thereby saving space. So we do not need to guess the whole set V1 up to Vc. And similarly, we do not need to guess the whole path. What we can do is we can guess them as we go along, and thereby we save space. Let us look at these ideas more clearly. So let V equals V1 up to Vn be the set of vertices in the graph. What we want to do is think about choosing a subset of size C from these vertices. A subset can be encoded as a 0, 1 vector. Let us say that we take a vector G1, G2 up to Gn, which is a 0, 1 vector. Then we can define a subset capital G to be the set of all Vi such that Gi equals 1. And this would be a subset of V. So here's our guess set. The way we guess it is by guessing each individual bit for each vertex. If the bit turns out to be 1, then that vertex is in the set, otherwise it's not. What we can do is guess the current bit of this vector one at a time. Thus, if Gi is equal to 1, we are guessing that vertex to be inside our set. And if it turns out to be 0, we're guessing it to be outside our set. Also, as we previously did, we can forget about all the previous bits of this bit vector and only remember the number of them which were in G, and that way we'll keep track of the size of G at the end of the loop. We'll find out how big our guess set was. So now the idea is that we will guess one vertex of this set at a time, or we'll go through all the vertices of the graph and guess whether that vertex is in the set or out. If we guess that this vertex is in the set, then we'll try to guess the path from S to this vertex, but this path will guess one vertex at a time. And if we verify that this vertex is in, so we have to guess it's in and be able to verify it's in, then we'll continue. If we are not able to verify, we will reject. If we guess that this vertex is out, we'll skip the verification path. And we will keep looking at these vertices, and at the end, if exactly C vertices were counted and none of them was T, then S is not reachable. From S, T is not reachable, and therefore we can safely accept. And this is all going to take log space. Let's have a look at the detailed algorithm. So we set a counter. So the input to the algorithm is as it was before. We set a counter D is equal to 0. And now for each vertex X in V, we will guess a bit G. If G is equal to 1, then the algorithm is guessing that X is inside this set, that we are guessing that X is actually connected to S. Now what we will do is we'll run the previous path verification algorithm. We'll set the current vertex to be S, and for n times we'll keep guessing the next vertex. If the next vertex is connected to the current vertex via an edge, we will continue. If we ever hit X, we'll exit out of this loop. Otherwise, we'll go on and guess the next vertex on the path. At the end of the loop, if X is equal to T, then actually what happened, we were able to find a path from S to T, and therefore we must reject. If that's not the case, we will count as one vertex was verified to be reachable from S, namely the vertex X. When this loop ends, we will look at our counter. If the counter has reached C, then we have verified that at least C vertices are reachable from S and none of them is T, and therefore we would accept. So in the algorithm, you'd see that D is being incremented, and at the end we check if D is equal to C, then we accept the input. So this is a very complicated algorithm, but if we stare at this algorithm, if we look at it, we realize that the algorithm is only using 2 counters, and therefore it's not using very much space. In fact, it's just using logarithmic amount of space. So far we have seen that we can solve the path complement problem provided we are given this extra information, this magic number that we call C. C counts the number of vertices that are reachable from S. In the next lecture, what we will do is we will start with this algorithm and we'll remove the restriction that we have put. We'll remove the restriction of the extra information. That algorithm is going to be more complicated, but it's going to use the same ideas and similar reasoning that we used to design this algorithm. It's going to be a wonderful algorithm. We'll look at it next time. So I'll see you next time. Thank you and goodbye.